Swayam Prabha. Digital India. Educated India.
Hello, I welcome you all in the course on refrigeration and air conditioning. Today we will cover the air refrigeration cycle. Now in today's lecture we will be covering Joule-Brayton cycle, Bell-Coleman cycle, and we will try to find COP of Bell-Coleman cycle. Now starting with the Joule-Brayton cycle, actually Joule-Brayton cycle is a air standard cycle for power generation, and this cycle is being used for the power generation in gas turbines. It has one specific applications in gas turbine, and in this cycle there are two isentropic processes and there are two constant pressure processes. So this cycle is depicted here on pressure volume diagram, and at the same time this cycle is also depicted here on temperature entropy diagram. Now in this cycle, first air is the working fluid, and the first air is compressed from state 1 to state 2 through a compressor. At state 2, constant pressure heat addition takes place. Normally in the gas turbines there is a separate combustion chamber. In that combustion chamber the heat addition takes place, but since it is an air standard cycle, it is assumed that throughout the cycle air is a working fluid. So from state 1 to state 2, compression of air takes place. State 2 to state 3, constant pressure heat addition takes place, constant pressure heat addition to air takes place, and when the state 3 is attained, the expansion of air takes place and we attain the state 4. During this process, the net output of the cycle is the area of PV diagram under 1, 2, 3, 4. This cycle can also be shown on temperature entropy diagram. Process 1 to 2 is isentropic compression, where work is done by the compressor on the air. Process 2 to 3 is constant pressure heat addition. Process 3 to 4 is output of the turbine or expansion of hot air takes place, and process 4 to 1 is the cooling process, or if it is open cycle, then at state 4 the air is thrown to the surroundings. Now if we reverse this cycle, reverse means instead of expansion in process 3 to 4, compression in process 4 to 3 takes place. Compression and then heat rejection, then 2 to 1 expansion and 1 to 4 heating. The cycle will become something like this. Now this is reverse Joule-Brayton cycle, or it is called Bell-Coleman cycle. Bell-Coleman air refrigeration cycle. It is called air refrigeration cycle because in this cycle air is the working fluid or air is the refrigerant. Now in this cycle, if we show it on the PV diagram, first of all compression of air takes place from state 1 to state 2. Now after this compression, the cooling of air takes place or heat is removed during this process from the air. So the temperature of the air goes down. When the state 3 is attained, again expansion takes place inside an expander. It is a turbine or an expander where expansion takes place, and these two processes 3 to 4 and 1 to 2 are isentropic process, and 4 to 1 process where heat is taken from the surroundings, and this process 4 to 1 produces the cooling effect. Now if I want to show the same cycle on temperature entropy diagram, then there are two constant pressure processes, constant pressure lines. Process 1 to 2, isentropic compression, where the pressure increases, then heat is extracted from the air, high pressure air. So, it becomes high pressure low temperature air and heat is taken away from here and we attain state 3. At state 3 again the expansion takes place and state 4 is attained. Now, I will give you some numerical values for these states also, so that you will have fairly good idea about the cycle. Now, starting from state 1, suppose the air is available at 27 degree centigrade and 1 bar pressure. So, when air is available at 27 degree centigrade, it is equivalent to 300 Kelvin of temperature. Suppose this air is compressed in a compressor having compression ratio of 4. So, P2 by P1 is 4. P2 by P1. Now, temperature at state 2 is going to be T1 multiplied by P2 by P1 raised to power gamma minus 1 over gamma. Because it is following the process, PV raised to power gamma is equal to constant, where gamma is equal to 1.4 for air. Now, if we put the numerical values at T1 is 300 Kelvin, so in order to find T2, T1 is 300 Kelvin, P2 by P1 is 4, 4 raised to power 1.4 minus 1 divided by 1.4. It will turn out to be 4 approximately 446 Kelvin. Approximately it is exactly it is 445.97, let us assume 446 Kelvin. So, 446 Kelvin is equal to 173 degree centigrade. So, the temperature of the air has increased during the compression process to 173 degree centigrade. Now, if I cool this air with the help of surrounding air is 27 degree centigrade. I cool this air to, let us say, 77 degree centigrade. So, it is T3 is 77 degree centigrade or 350 Kelvin. Temperature of air available at state 3 is 350 Kelvin and pressure is 4 bar. Here pressure is 1 bar, here pressure is 4 bar. Now, if I expand this air to state 4, if I expand this air 350 Kelvin air at 4 bar to 1 bar isentropically, in that case I am going to get T4 is equal to T3 P4 by P3 raised to power 1.4 minus 1 1.4, and this, just a minute, it raised to power gamma minus 1 over gamma. Now, T3 is 300, T4 is equal to T3, T3 is 350 Kelvin, 350, and P4 by P3 is 1 by 4 and this gamma 1.4 minus 0.4 divided by 1.4. So, this will turn out to be approximately 235.44 Kelvin, or let us say 235 Kelvin, or is equal to minus 38 degrees centigrade. So, during this cycle, we have taken outside air, compressed it, cooled it, and then we again is expanded back to the same pressure 1 bar, and the temperature of air has reduced to minus 38 degree centigrade, which is very, very low. So, with the help of this Bell-Coleman cycle, we can get very low temperature in the case of air. Now, after this, we will try to find the performance of this cycle. In order to find the performance of this cycle, we should know how much heat transfer is taking place and how much energy is consumed in compressing the air. During refrigeration process, that is 4 to 1, the heat transfer is, that is QL, is a Cp, this is specific heat of air at constant pressure, T1 minus T4. This is the refrigeration effect we are getting this cycle. Now, how much work is consumed? The work consumed is area of PV diagram or work in compression minus work gained in expansion. Now, compressor work from state 1 to state 2. There are several ways of doing it. First of all, it is a cyclic process. So, in a cyclic process, as per the first law of thermodynamics, cyclic integral of delta Q is equal to cyclic integral of delta W. Here, in these two processes, process 1 to 2 and 3 to 4, they are isentropic processes, so heat transfer is 0. Only heat transfer is taking place in process 4 to 1 and 2 to 3. So, net heat transfer is Cp T2 minus T3 Cp T1 minus T4, and this net heat transfer is also net work transfer. That is one way of doing it. Another way is, if we use the formula delta W is integral of 1 to 2 V dP. Through this formula also we can find the work done, because when these processes are not isentropic, in that case we cannot use this formula. This formula is applicable only in the case when all the processes are ideal and there is no heat transfer during these two processes. So, in order to have a generalized expression, let us try to find out work through this formula, work consumed by the compressor through this formula. This work interaction has negative sign and energy is consumed by the compressor. It means work interaction is negative in this process. So, negative is possible, so positive. So, the work of the compressor is state 1 to state 2 V dP. During the compression, it is isentropic compression or reversible adiabatic compression. PV raised to power gamma will remain constant, or V is equal to C raised to power 1 by gamma and P raised to power minus 1 by gamma. Now, putting this value of V here, we will get work of the compressor is equal to integral from 1 to 2 C raised to power 1 by gamma P raised to power minus 1 by gamma dP. Again, the work of compressor is equal to C raised to power 1 by gamma, and if we integrate this, we will be getting P 1 minus 1 by gamma divided by 1 minus 1 by gamma 1 to 2, or gamma over gamma minus 1 P2 raised to power gamma minus 1 over gamma minus P1 raised to power gamma minus 1 over gamma multiplied by C raised to power 1 by gamma. Now, C raised to power 1 by gamma is equal to P raised to power 1 by gamma into V. Now, putting this value, because now PV, now we can always take it as like this, P1 raised to power 1 by gamma V1 is equal to P2 raised to power 1 by gamma V2. Now, putting this value of C here, we will be getting gamma over gamma minus 1 P2 1 by gamma P2 gamma minus 1 by gamma V2 minus P1 1 by gamma, or we can, instead of writing like this gamma minus 1 over gamma, I will write 1 minus 1 over gamma, 1 minus 1 over gamma and V1. If you simplify this equation, you will be getting work consumed by the compressor is gamma over gamma minus 1 P2 V2 minus P1 V1. Air is considered to be an ideal gas here, so PV can also be replaced by RT. So, gamma over gamma minus 1 R T2 minus T1. Now, gamma over gamma minus 1 into R is nothing but Cp, Cp T2 minus T1. Here there is an interesting observation that adiabatic compression is taking place, pressure of the gas is rising, okay, and work done in this process is Cp delta T. Cp is the heat addition, specific heat at constant pressure. It is Cp dt and there is no constant pressure process here. So, it is only an expression. It does not indicate that the process is a constant pressure process, but this expression is a simple expression for work consumed by the compressor. Similarly, we can find the work output during process 3 to 4, that is work of the turbine or work of the expander is equal to Cp T3 minus T4, and the net work is Cp T2 minus T1 minus Cp T3 minus T4 or Cp T2 minus T3 minus Cp T1 minus T4, or heat rejected in this process and heat taken in this process, or cyclic integral of heat transfer. There is another way of, I have already discussed two ways of finding the network. There is another method also, if you use the first law of open system. First law of open system states that in an open system, delta Q minus delta W is equal to dH plus CdC plus GdZ. Now, here in this case, in case of compressor, this change in potential energy can be considered as 0, change in kinetic energy is also 0, isentropic process, there is no heat transfer. So, minus delta W is dH. This minus delta W means work is consumed by the compressor. So, work of the compressor is integral of 1 to 2 dH. As we know that H is equal to internal energy plus PV, or H is equal to U plus RT. PV, we can always use the relation PV is equal to RT in case of ideal gas, and air is assumed to be an ideal gas. So, dH is equal to du plus R dt, or du is always CV dt plus R dt, and this is CV plus R dt, and this is, so dH is equal to Cp dt, or H2 minus H1 is equal to Cp T2 minus T1. Similarly, we can derive for this also that work attained during expansion process is Cp T3 minus T4, and we can again come to the conclusion, or we will come to the same expression as we have attained through earlier processes. So, we have three alternative methods to find work during compression. Now, COP of this cycle, coefficient of performance of this cycle, because efficiency of any refrigeration cycle is judged by the coefficient of performance. So, coefficient of performance is heat transfer during refrigeration process, that is Cp T1 minus T4 divided by net work consumed. So, it is going to be Cp T2 minus T1 minus Cp T3 minus T4. Now, Cp will be cancelled out and COP will remain T1 minus T4 divided by T2 minus T1 minus T3 minus T4. If we rearrange these terms, T1 minus T4 shall be equal to T2 minus T3 minus T1 minus T4, or it is equal to 1 by T2 minus T3 divided by T1 minus T4 minus 1. We can further simplify this. We can further simplify because P2 by P1 is equal to raised to power gamma minus 1 over gamma is equal to T2 by T1. This is also P2 and this is P1. So, P2 by P1 is equal to T2 by T1, this is from ideal gas relation, is equal to T3 by T4. Now, here if we take this relation, or we can further manipulate it like this, T2 by T3 is equal to T1 by T4. So, T2 by T3 minus 1 is equal to T1 by T4 minus 1, T2 minus T3 by T3 is equal to T1 minus T4 divided by T4, or T2 minus T3 divided by T1 minus T4 is equal to T3 by T4, or T2 by T1. Now, this T2 minus T3 divided by T1 minus T4 can be substituted here, and we can get the value of COP as 1 by T2 by T1 minus 1, and final expression for COP as T1 by T2 minus T1. So, for ideal Bell-Coleman cycle, we need only two information: temperature after compression and temperature before compression, and we can find the COP of the cycle. Actual cycle. Now, in actual cycle, I will depict the actual cycle on both on pressure entropy, this pressure volume and temperature entropy diagram. In actual cycle, first of all, this is ideal cycle. 1, 2, 3, 4. Pressure and volume. In actual cycle, this is no longer an adiabatic process. The process will be something like this. It can be shown here as change in the entropy has increased during this process. So, it is 2 dash. For cooling also, temperature may not remain constant. Okay. So, for cooling, the pressure may not remain constant. So, pressure will fall during cooling process. And after that, expansion also is not an isentropic process. It is again there is a change in entropy. So, the expansion will be something like this: 1, 2 dash, 3 dash and 4 dash, and there is going to be a pressure drop in the evaporator or during the heat extraction from the surroundings also. This is the actual cycle. So, the pressure at the outside of the expander is greater than the pressure of the inlet of the compressor. Now, with this I end this lecture. In the next class, we will take up aircraft refrigeration system.